let's just talk the SI units, which is basically a standardization that we've done in science and engineering to get around political pressures, if you will. Historically, different countries use different units, and that posed a problem because if I worked in country A that used system A, and I did my own calculations, if I want to share it with somebody in country B that used system B, that's not as easy. They have to convert everything, and that's just a pain. So what we did in engineering and in science said, the heck with all this. Let's all, as scientists and engineers, be our own society, if you will, and use our own the units that we are going to say are standard. And so we standardized it. And SI is a French acronym for International System. And there are 7 basic units from which we derive everything else. Okay? And this mostly metric. It's not necessarily everything here is metric, but mostly here is metric. Length we define as a meter. Okay, not inches, not feet. Mass is the kilogram, even though you think it may be the gram, it is not. It's the kilogram. Time would be second. Temperature will be Kelvin. Amount of substance will be mole, which we'll discuss in a whole different lecture. Electric current, which we won't use in this class, is the ampere. And luminous intensity, which we won't use in this class, is the candela, so CD. Okay, these are the basic units. Everything else is derived from that. So if you're talking about speed, for example, which is, like your car going 50 miles an hour, in SI units, it will be meters per second. Okay, but it's just derived from this. So things like a force, Newton, for example, that's derived from these things. Things like PSI, that's pounds per square inch. We derive from these basic units of length, mass, time, current, temperature, substance, and luminous intensity. Everything is derived from these 7 basic units. We also have prefixes in SI units, and so if I attach one of these symbols to one of these, I can indicate that I'm dealing with something that's a little larger or a little smaller. So if I take a meter and I attach, say, a C to the beginning of it, so maybe here. So if I have 5, you've all seen this, 5 cm. C indicates to me here that it's 10 to the minus 2. So this C here means that it's 10 to the minus 2, and this thing is still meters. So it just tells me that it's 5 times 10 to the minus 2 meters. It's 5 centimeters, okay? And I could do that with any of them. So gigameter, if I do 5 gigameter, okay, all it says is that this G here is 10 to the 9th. So I have 5 billion meters, okay? And so any of these is fair game for you. You should know. And throughout your career as scientists and engineers, you will probably remember these anyway, because you'll use them so often, right? So let's talk a little bit definition. Length is just when you measure distance between 2 spots. Mass is how much of a material you have. You put on a scale, you measure the amount of it that way. Temperature. This is a little bit different, and so I'm going to try to define this for you now. This is basically, imagine I look at a material under a microscope, okay, and I look at it at time equals, 3 seconds. And then I look at it again at time equals 13 seconds, so 10 seconds later. So at first, maybe it's got 5 molecules in it. 1, 2, 3, 4, 5. Okay, and then after 10 seconds, maybe it will look like this. It moved, as you imagine. The 5 molecules moved around. And maybe later on it will move even more. Something like that. Okay, so I have this is maybe a t is equal to 23 seconds. So they move around. They're having a party. So I'm gonna call that like a dancing energy. That's what basically how much they're moving around, and they're moving in there, and they're touching each other, and they're flying everywhere. That's what molecules do. And the how fast this changes dictates how hot the material is. If I look at another material under the same conditions and it's got 5 molecules and it looks like this, and after 10 seconds it looks like this, and after 10 seconds it looks like this, that means to me that They didn't really move much. They have very low energy. And temperature is defined as, temperature is, in the actual definition, is the average kinetic energy of molecules. So kinetic energy means energy of motion. How much energy is given to their motion over time, okay? So it's how hot they are. So if I look at a material and it moved a whole lot, that means it's very hot. It's got a lot of high temperature. If it doesn't move a lot, the molecules don't move much, it's very cold, all right? So that's basically the idea there, okay? The SI unit for temperature is the Kelvin, which, by the way, your homepage on Google can report the temperature outside in Kelvin for some reason. And it is related to the Celsius linearly. So if I know degrees Celsius, I can find Kelvin very easily. And it's the absolute temperature. Okay. What do I mean by that? So if I'm telling you right now that it's 10 degrees Fahrenheit, which sucks because it's really cold. And then I tell you it's 20 degrees Fahrenheit the next day. Can you say it's twice as hot? The answer is no. It's not an absolute temperature. Fahrenheit and Celsius are not, sorry, Fahrenheit and Celsius, yes. F and C, not absolute. So I can't do that. But Kelvin is. Kelvin definitely is. So if I tell you right now it's 100K, which you don't want to live in that, trust me. And then the next day is 200K, still don't want to live there. I can say that this is twice as hot. Yes, this is twice as hot. Yes, that is true. This is true. Kelvin, I could do that. Celsius and Fahrenheit, I can't do that. That's why it's useful for you scientists and engineers to deal with Kelvin, because I can actually treat stuff like that, right? It's absolute. So if I know that water freezes at 0 degrees Celsius, right? So 0 degrees Celsius is 273 degrees Fahrenheit. Kelvin. 273 Kelvin. So 0 Celsius is 273 Kelvin. Right? I can convert from Fahrenheit to Celsius too. So we use Fahrenheit here in the United States. So let's say it's 41 degrees out. There's a mistake here. So this should be 9 here. This should be 5. So I'm correcting it right in front of you because this is bad. Okay. I don't know why it was like that. All right. So let's go back there. If it's 41 degrees outside right now, Fahrenheit, okay? I subtract 32, okay? And that's 9. 9 divided by 9 goes away, and so I have 5. 5 degrees Celsius is exactly 41 degrees Fahrenheit. That's how you would do that, okay? I could go from the other way around, from Celsius to Fahrenheit. So if I give you the degrees Celsius, I'll say it's 5 degrees Celsius right now. 5 divided by 5 would be 1, times 9 would be 9, plus 32 would be 41 degrees Fahrenheit. So it's exactly the same, okay? This, don't worry about it for this class. You will see this. If you're an engineer, you'll see this. Otherwise, don't worry about this. This is the imperial version of absolute temperature. It's called the Rankine. Okay, so 100 Rankine is twice as hot as 50 Rankine. And this is how you convert to that. So, but don't worry, we're not going to use this. Don't commit this equation to memory. Don't worry about this equation unless you're specifically interested in that. Not for this class. I just want to show it to you that it does exist, and we do have another absolute temperature. Okay, let's do some example with temperature conversions. All right. So I know that the boiling point, the lowest boiling point of all elements, is that of helium, meaning that helium can turn into a liquid, believe it or not. So that stuff in balloons can turn into a liquid, but it does so. The boiling point for helium is negative 452 degrees Fahrenheit. I want this in absolute temperature in Kelvin. So convert to Kelvin. which is the absolute temperature for this. Okay, so how would I do that? All right, so to do this, I need to utilize my equations for that I just showed you. So let me go back here. So I know that Kelvin, I can relate it to Celsius, not to Fahrenheit. But I can relate Fahrenheit to Celsius. So my goal here is to go from Fahrenheit to Celsius using this. And then afterwards, taking the Celsius and putting in here, and then get Kelvin. Okay, so first, convert degrees Fahrenheit to degrees Celsius. And then second, takes degrees Celsius and go to Kelvin. All right, so how do I get from degrees Fahrenheit to degrees Celsius? If I look here, I want degrees Celsius, so I'm going to use the second equation here. Degrees Celsius is 5/9 times degrees Fahrenheit minus 32, right? So I'm going to put in the number here that I have, negative 452. So degrees Celsius would be 5/9. Negative 452 minus 32, and if I punch it into a calculator, I get that my degrees Celsius is negative 269 degrees Celsius. Now I still want Kelvin. Okay, so Kelvin is going to be degrees Celsius plus 273, right? So I'll just put that in here. And I get that Kelvin is negative 269 degrees plus 273.15. And when I add them up, well, I get 4.15 Kelvin. Okay. I should mention there is no such thing as negative temperature when you're talking Kelvin. 0 Kelvin is the lowest temperature you'll see. It's known as the absolute. It is known as absolute zero. So this is very close to absolute zero. And indeed, if you want to have liquid helium, you have to go really cold to almost absolute zero. So that's how you do that. Let's do another one. Let's see. Let's try to convert. No. Yeah, you know what? Let's do that. Convert. Let's see, temperature that we see in this town, much more. 95 degrees Fahrenheit to Celsius. Okay, so convert 95 degrees Fahrenheit to Celsius. All right, so 95 Fahrenheit to Celsius. I want Celsius. Again, looking at this equation, it's the second top right here. 5/9 times F minus 32. So, I mean, I chose this on purpose. And so degrees Celsius here would be 5/9 times 95 minus 32, right? And this minus this is 63. 63/9 is 7. So there you go. It's 35 degrees Celsius. Okay? So that's how you go about to convert.